All right, so now that we've learned all of the double angle identities for cosine, sine, and tangent, we're going to apply them. Why do we need these identities? So here with our first example, and so hopefully you are doing this in your notes. All of the notes are online as usual, but if you want to follow along and write these down as we go, you sure can. So we are told that cosine of x is 0.3. Remember that that's a ratio, so the cosine at some angle x has a ratio of 0.3. I want to know, without having to find the angle necessarily, what the exact value of the cosine of 2x would be. So let's think about what we know so far. I have some angle x for cosine, and I have a positive ratio. So that would either be in the first or in the fourth quadrant. So I'm just going to go ahead and draw this in the first quadrant, and we'll call this angle x. I want to find the exact value of the cosine of twice that angle. So wherever this angle is, twice of that would be, I don't know, somewhere around here, and I'm not drawing this to scale. Okay, so this would be 2 of whatever this angle x is. Well, I know that the ratio for cosine at this angle is 3/10, and so I want to find the exact ratio for this 2x angle. And so I'm going to use one of these identities, and I don't know the ratio for sine. I could find it, but I'm just going to use this equation right here, this identity, since it only has cosine in it. So I'm going to rewrite this as the cosine of 2x, and that equals 2 times the cosine squared at that angle x minus 1. And so since I know that the cosine at x is 3/10, I can replace this cosine with 3/10. I know that this ratio is 3/10, so I'm going to replace it with that. So next order of operations, I'm going to square that value. So I'm going to get 9 over 100. Now I'm going to multiply by 2, so 18 over 100. And I'm going to rewrite this 1 as a 100 over 100. Now that I have a common denominator, I can subtract straight across, and I'm going to end up getting negative 82 over 100. And that is an exact value, an exact ratio. Now let's say that we wanted to check our answer. I could find this angle by taking the cosine inverse of 0.3. So I'll go ahead and take cosine inverse, and notice I'm in degree mode, which it doesn't matter. Cosine inverse of 0.3. And let's say that this angle x was 72 degrees-ish. Well, twice that would then be 145 degrees. So 2x is about 145 degrees. We were looking for the cosine's ratio at that angle. So I'm going to plug that angle into the cosine function. And this is what I get. Now I'm going to go ahead, and you can already see that they are going to be the same, but negative 82 over 100, pretty much the same number. This is the approximate value. This would be the exact. And so we just found an exact value for twice an angle, knowing the regular x's ratio. All right, so moving on to another example. We are going to manipulate these equations a little bit. And so let's say that we wanted to rewrite this identity. I have a 4 times a sine times a cosine. Well, notice none of these identities match that. This one looks the closest because there's a 2, but that's it. So I'm going to start with this one and try to manipulate it to figure out what 4 sine cosine would equal. So I'm going to start with a sine of 2 theta equal to 2 sine theta cosine theta. So to make this side look like the 4 sine cosine, I would have to multiply it by 2. Well, if I do it over here, since I know these two things are equal, I'm going to multiply over here by 2 as well. So I get 2 sine of 2 theta would equal 4 sine times cosine. Well, that means that this piece, we could use the double angle identity, and it would just equal 2 sine of 2 theta. So we rewrote it using a double angle identity, but since this 4 was twice of what it normally is, instead of it equaling sine of 2 theta, it equals 2 sine 2 theta. Okay, so we're going to do something like that again. I have a sine squared, and so I want to rewrite this using a double angle identity. Well, notice that the only identity with just a sine squared in it is this one right here. So I'm going to go ahead and start with that identity, and I know that the cosine of 2 theta equals 1 minus 2 sine squared of theta. And so I want to rewrite this using a double angle identity. So to solve for sine squared, I'm going to first subtract 1. So I'll have the cosine of 2 theta minus 1 equals negative 2 sine squared theta. From here, to get this sine squared by itself, I would divide everything by a negative 2. So I'm going to end up getting a negative 1/2 cosine 2 theta. Negative divided by a negative is a positive 1/2. That's what sine squared would equal in terms of a double angle identity. So I could rewrite sine squared as negative 1/2 cosine of 2x plus 1/2. Okay, so we're just manipulating these identities to look a little bit different. All right, next slide we're going to look at. Okay, so now, similar goal, I want to rewrite cosine squared using a double angle identity. So looking at my double angle identities, the only one that involves just a cosine squared is this third identity for cosine 2 theta. So we will start with the cosine of 2 theta is equal to 2 cosine squared theta minus 1. And again, we want to isolate the cosine squared. So we're going to start by adding 1 to both sides. So I get cosine of 2 theta plus 1 equals 2 cosine squared. I would now have to divide both sides by 2 and divide every single thing by 2. So I would get 1/2 cosine 2 theta plus 1/2 equals, now we have the cosine squared alone. So how I could rewrite this cosine squared is 1/2 cosine 2 theta plus 1/2. So just manipulated that identity a little bit. All right, so where we are going to need this is when we are solving equations. So you could do this problem in 2 ways. One way, since I only have a cosine squared equal to 0.5, is I could start out by just square rooting both sides. And this is probably going to be the easier method. So I will then be left with a cosine theta equals the square root of 1/2. And that would be plus or minus. Anytime you square root both sides of the equation, you have 2 answers. Well, another way that you could rewrite this, and this would make this method a little bit harder, is I can rewrite this then as the square root of 1 over the square root of 2, which is plus or minus 1 over the square root of 2, which is not rationalized, and so after it is rationalized, I will get plus or minus square roots 2 over 2. And so we're looking for all of the angles where cosine would equal positive and negative square root of 2 over 2 in between 0 and 360. So if you look to your unit circle, that's going to be in every quadrant at the increments of wherever reference angles are 45 degrees. And so my answers for theta would be 45 degrees, 135 degrees, 225 degrees, and 315 degrees. So that is one way that you could solve this equation. Another way that you could solve the equation is using one of the double angle identities. And so I could isolate this cosine squared right here, which is what we already did. And we found out on the previous slide that I could replace a cosine squared with a 1/2 cosine 2 theta plus 1/2. So I'm going to go ahead and rewrite that side with a 1/2 cosine 2 theta plus 1/2 is equal to 0.5. So now in solving this equation, I would subtract over the half, which is actually going to turn into a 0 when I subtract that 1/2 over. Now I would multiply both sides by 2 to get rid of this half. Well, 0 times 2 is 0. So I'm looking for where cosine of 2 theta would equal 0. Well, if you think about our unit circle, cosine is 0. That's when x is 0, so that is at 90 degrees and also at 270 degrees. But keep in mind, this is a 2 theta, so 2 theta needs to equal 90 degrees, or 2 theta needs to equal 270 degrees. Divide both of these answers by 2, and I end up getting theta is 45 degrees, and theta will then be 135 degrees. Well, normally to find more answers, I would add and subtract 360 to each of these. However, since this 2 is right here, my period is no longer 360, it is 180. And so I could add 180 to each of these answers, and I will end up getting then from here 225 degrees as well as 315 degrees, which matches what we just solved for using the other method. So either of these methods would work. This is one way where we could use the double angle identities. However, we don't have to. As always, it's a good idea to check a graph. And so you can see that our answers between 0 and 360, where the left side of the equation equaled 0.5, was at 45, 135, 225, and 315. All right, so we are going to put one more example in our notes. And it is another one where we need to solve an equation in the interval 0 to 2 pi. So note that we are in radians now. And my equation is set up for sine times cosine equals the square root of 3. So on a previous slide, we just looked at how we could manipulate this 4 sine cosine. And so I could rewrite it as 2 times 2 sine x cosine x equal to the square root of 3. And then this right here can be replaced with a sine of 2 theta. So as this equation is right now, I have 2 different trig functions, and so I'm not going to be able to solve it. But I can replace this with 2 times sine of 2 theta, and that's equal to the square root of 3. Now to get sine alone, I would divide both sides by 2, so I'm going to get sine of 2 theta equals square root of 3 over 2. I'm hoping that now this ratio is kind of ringing some bells and that you realize that this is a value on our unit circle, and sine is the square root of 3 over 2 at 60 degrees. And keep in mind, sine is also positive in the second quadrant, and so that would then put us at 120 degrees. Now keep in mind that we are in radians, and so this would actually be pi over 3 and 2 pi over 3. All right, something that we need to keep in mind, though, is that this is a 2 theta. So 2 theta needs to equal pi over 3, or 2 theta would need to equal 2 pi over 3. So we would divide both of these answers by 2, and we would end up getting a pi over 6, and over here we would end up getting a pi over 3. Half of 60 degrees is 30 degrees, which is pi over 6. Half of 120 is 60, which is pi over 3. Now, if we look at the graph, we can see that in between 0 and 2 pi, that I should have 1, 2, 3, 4 answers. In radians, we typically add increments of 2 pi to get more. However, this is a 2 theta, which means that the period is no longer pi. The period is going to be, the period is no longer 2 pi, the period is half that, which is pi. That's because of that 2 right in there. So I can add increments of pi to each of these to get more answers. And so if I added pi to pi over 6, and hopefully you're looking at your unit circle, that would end up giving me 7 pi over 6. Over here, I would end up getting 4 pi over 3. So we get 4 pi over 3, pi over 3, pi over 6, 7 pi over 6 will end up being my 4 answers in the domain 0 to 2 pi. So here's pi over 3, half that's pi over 6. This guy would then represent, here's 4 pi over 3, so then this would represent the 7 pi over 6. And so we found all 4 answers, and again, the whole reason for these double angle identities is to help us solve an equation when we're in one where we have 2 different trig functions and we need to rewrite it. Okay, this is all of the notes for today. Homework section 8.6 is going to be due on Thursday night. It has been open for a while, so try that. We will finish up notes tomorrow, and then we will have a homework day Wednesday, review Thursday, and then test on Friday. See you all tomorrow.